Welcome to the office. I want to take a really brief look at just a few theorems and definitions, essentially, that we need to familiarize ourselves with. They'll be helpful, I believe, as we again move forward in content. And they're just some key takeaways from what we want. Not that we will understand greatly how to use them, but as we look to wrap up our content coverage, this is going to be one of the things that we would like to be able to bring forward with us into future classes as well. Just looking for that continuation there. So let's take a look at our notes, of course. We're looking at the fundamental homomorphism theorem. So we'll get to that for our second theorem here. Let H be a normal subgroup of G. Then gamma, a function from G to G mod H, given by gamma of X is equal to XH, right, that coset, is a homomorphism with kernel H. So why is that useful? Well, right, I mean, it's a little bit silly, but I think the most useful bit about this is the fact that we have now identified a way of describing every normal subgroup as a kernel of a homomorphism. Now we have to have normal before we can have this guy, so it's a little bit of a circular situation here. But anyway, we can observe each normal subgroup as the kernel of some homomorphism. So that's kind of cool. All right, I also want to use that in our next theorem as well. So we're bringing that forward into the next theorem. So the fundamental homomorphism theorem, how about half, maybe 3/4 of this we've already said before. So let phi be a group homomorphism from G to G prime with kernel H. Then phi of G is a group. We've already said that the image of subgroup or a group is a group. We looked at that a little while ago for a homomorphism. And mu, the function that we took a look at a little while ago, that is an isomorphism from G mod H to the image of G under phi, given by exactly this. That is an isomorphism. And then now, if gamma is a function from G to G mod H, that is a homomorphism given by this. Then this is essentially the new thing here, right? Because we just defined that. We can actually define phi in terms of mu and gamma. So what does that really tell us? Well, let's take a look at a kind of a visual representation here. So I have my group G, and I have my homomorphism phi, and I can move to the image phi of G. No surprise there. But what I can do is I can move from G actually into G mod H. Right, here we are. And what function did that? Well, moving from G to G mod H is the gamma function. So this is the gamma function. And then we can move from G mod H into phi of G by the function mu. That's the function mu. Here we are. So we can observe, again, we're looking to observe phi as the composition of first apply gamma and then apply mu to gamma. So there we go. That will work. So that's really all that we're interested in observing here. Remember, mu is an isomorphism, gamma is a homomorphism, and phi is a homomorphism. And based on the way that they were defined, we can observe phi as a composition of those two. Fantastic. We may find that to be useful as we move forward. I'm not sure that I have any examples that make explicit use of this, but again, it's definitely a key takeaway. All right, so normal subgroups and inner automorphisms. I want to have a good understanding, I want to present a good understanding of normal subgroups. There are different ways that we can represent normal subgroups. The way that we have defined a subgroup to be normal is if the left and right cosets are the same. But if we have this sort of a situation here, right, if this is G times H1 is equal to H2 times G, right? This for all G in G, we can get this sort of a relationship. If we have this, then that can give us that G times H1 times G inverse is equal to H2. And this is exactly what it would look like for us to have condition 2. So we can see that 2 and 3 are equivalent. But in order for us to have this means explicitly that GHG inverse belongs in there, right? That's the definition for these two things to be equal to one another. And then, of course, if I have this particular scenario, this gives me that GHG inverse is equal to some other H, which I can multiply by G to get exactly this relationship, which brings us back to the third condition. So we have movement from our original definition of what it means to be normal into this version, and then back to our original version. So each of these conditions are equivalent to one another in determining or showing or defining that a subgroup is normal. So we want to have that in hand. That is helpful for us. All right. The last thing that I want to talk about before we consider a few more examples is just the idea of an inner automorphism. So first, an automorphism. What is an automorphism? Well, an automorphism is just an isomorphism of G with itself. Now, of course, I can just I can map everything to itself, and that's an isomorphism, right? Map G to G by B of A is equal to A for everything. So there is an automorphism of every group, right? It's a trivial automorphism. But what we can do is we can also create these automorphisms by conjugation, is what we call it, by some element. So if I have I sub G of X, I can take that element X multiplied by G on the left and G inverse on the right. Now, if we have that the group G is abelian, then of course we can rearrange G and G inverse cancel, and this is just the identity. So I inner automorphism, I identity, right? It's all kind of the same thing. But if we don't have commutativity, then we don't have that the G and G inverse cancel. So again, an inner automorphism. Of course, a product of elements inside of G is going to produce another element inside of G because G is a group, it's closed. So we know that this gives us elements in G. It can be shown that this is a one-to-one and onto, all of that sort of stuff. So inner automorphism. All right. So performing this function on X is called conjugation of X by G, and we can actually talk about conjugation of a group, which is what we're going to look at in, actually that's just the third part here, but we'll also look at that in our next example. All right, so if left coset and right coset are the same if and only if we have that the image of H is H under all automorphisms. Why? Well, because we have this equivalent condition given on the previous page. Right? Because of that condition, that equivalence condition for normal or having the equality of left and right cosets, then when we take that inner automorphism, we should get H back. So H is said to be invariant under this. That is, the image of H is H. So that is the case for all normal subgroups. We haven't said those words explicitly, but we've given all the conditions for that. The image of a normal subgroup under an inner automorphism is the same subgroup. All right, so note that this does not mean that it is acting in an identity fashion. We're not saying that G and G inverse will cancel out. We don't have that commutativity necessarily. We can end up switching things around, but it's just a permutation of elements within H. So I'm rearranging elements within H. I'm not fixing them. The whole subgroup is fixed, but not the individual elements within that subgroup. All right, and if the image of H for some subgroup Okay, if not necessarily or definitely would not be a normal subgroup, but if the image of H is some other subgroup, right? It's not guaranteed to be a subgroup. It's just actually a coset, right? So if we end up with something different, then K is said to be a conjugate subgroup of H, or something like a coset, I guess. But well, actually, here this is right. It's an automorphism, so it's an isomorphism. So it won't end up with another set. It's not a coset. I apologize. This will be another group because this is an automorphism, right? An isomorphism. That is an image of a subgroup under an isomorphism is another subgroup. So the image of a subgroup will be another subgroup. So if you do get something different, it's called a conjugate subgroup of H. All right, fantastic. I think that shares what we need to for now. We're going to take a look at, I think, 2, maybe 3 more examples. So just trying to get more exposure and experience with how do we manipulate these things within quotient groups. That's our last collection of examples. And then I want to take a look at some theorems and how do we manipulate, prove things, or show things within this content. So I'll see you guys back here in the office for some more examples.